Hello everyone, welcome to this lesson. So in this lesson we're going to go through the Python code for the trapezoidal rule. This code will give you the ability to find the area under the curve for any function you might be interested in, for any integration interval. In this case we dealt with the function ln of x between 2 and 4, and you also get to define the error criteria. So the error of the estimate that you're trying to calculate. For example, an estimate with an error, say below 0.1% or 0.001%. Now, before we go into the code, I want to recap briefly what is the trapezoidal rule. So the trapezoidal rule finds an estimate for an area under the curve for a given function for a certain interval using a first order polynomial, and we saw that the area under a first order polynomial is actually geometry of a trapezoid, which is where this technique got its name. We went through a single application, which is using one trapezoid, and also multiple application, which is using two or more. And we solidified this entire technique in this general equation where basically this gets you the estimate ranging from one trapezoid to however many trapezoids you need to get the error that you are interested in. So let's begin. So the first thing that I'm going to do is I'm going to define the function. I'm going to define it using a lambda expression, which is an anonymous function. And the independent variable is x, and we can use the math package to call the ln function. And let's actually import for this reason the math package. And in the math package, actually log of x is base e, which in fact log of x in the math is in fact ln of x. So given that I have defined my function, let's actually define the integration limits. So we know that we are integrating between a equal to 2 and also b equal to 4. So given that I have defined my function integration limit, let's actually code the basis of this technique, which is basically this function. And we're going to be using a while loop, and a while loop because we want to be looping until a criteria is met. In this case, the approximate error to be less than 0.1%, which is going to be the first error that we're going to be examining. So the approximate error here, 0.1%. So this entire loop is dependent upon the coding of this function. So this function is dependent on h, the summation code, and also the function value at the lower limit and the function value at the upper limit. So let's actually start by coding h. Now h is the number of segments, and h is defined as equal to b minus a divided by n. Now we have h, so let's actually go ahead and code the sum function. So sum, let's actually initialize the sum to be equal to 0, and we can use a for loop for I in range, and in this case we see that the sum is defined from I equal 1 to n minus 1, so the range is going to be 1 to n. Now the reason I'm using n and not n minus 1 is because the range function starts from the first element all the way to the last element, but not including the last element, which means it in fact actually stops at n minus 1. So you have one of two ways to write a sum code. You can either do sum is equal to sum plus, or there is a cleaner shorthand notation where you can actually add the plus here and get rid of all of that. So the remaining here, we're going to have 2 multiplied by f of xi. So we have 2 here multiplied by f of xi, and xi is going to be defined as a plus I multiplied by h. Now to understand how xi is calculated, let's actually take an example. For example, the two trapezoids here. We know xi here is 3. Here, since we have only one loop here, because it's 1 to 1, here we have I is 1, and also h, since we have two trapezoids, h is going to be 1, so it's going to be 2 plus I multiplied by h, so plus 1 multiplied by 1, so that's going to be f of 3. So given that I have h and given that I have the sum, let's actually add the function value at the lower limit and the upper limit to get an estimate for the integral. So the integral is going to be equal to h divided by 2 multiplied by the function value at a plus the sum that we have calculated plus the function value at b. Now, at this point, we have actually created the first estimation. Now, before we go to the next iteration, we're going to have to define what the approximate error is, because when it goes to the next loop, it's going to have to decide, is the approximate error greater than or equal to 0.1 to decide whether or not it's going to continue looping or break out of the function. So we know that the approximate error is defined as the absolute, and it's the new minus the old divided by the new. So in this case, the new is defined as integral minus the old divided by the new. And since we're dealing with a percentage, let's multiply this by 100. Also, since we have the true value here at 2.15888, let's actually create a code for that as well. Let's actually change this to T. I'm going to change this to 2.15888, and here 2.15888, and this is compared to the current approximation, which is the integral. Now, before we also go to the next loop, we're going to have to store the current estimate for the next iteration, because for every iteration you're going to have to be calculating the approximate error. So since when you're looping, this value in the integral is going to be replaced, you need to store the current value in another variable so you can actually calculate the approximate error for the next iteration. So let's actually store the current estimate, which is in integral. Let's actually store it in old. And also, before we go to the next loop, we're going to have to increase the number of trapezoids to get a better approximation. So again, either you can do n is equal to n plus 1, or I'm just going to use the shorthand notation plus equal to 1. So at this point, we are done with the code. The only thing that I need is to initialize a few values. So I'm going to initialize the approximate error here to be 100. And also I need to initialize n to start at 1 trapezoid. And also I need to initialize the old at 100 arbitrarily. So at this point, the only thing remaining is we need a sum code, or not a sum code, a print code, so we can actually see the numbers and see how our estimates are doing. So for ease, I actually created a sum code here, so I'm going to paste it up here and explain how it works. So this is a display code. It prints the header, so I wanted to see the number of trapezoids for each iteration, and also the approximate error, the true error, and the current approximation. Now the \t are just tabs to make sure that the header lines up with the information. So let's actually run this and I'll show you how it looks like. So we have n, we have tab, ea, tab, et, tab, and integral. So let's actually take the actual display code, and I will place it here. So this is a string format, so the %f is the placeholder. So the first %f will put whatever you put here in it, so in this case it's going to be put n, and the second %f, ea, third et, and fourth is going to put the integral. And again, \t is just tab to make sure that everything lines up when I run the code. So at this point, we have coded the function, we have defined the integrals, we have also created the loop where it defines h, the sum, and here it combines the basically the equation for the trapezoidal rule. We created the approximate error, which the loop is defined in. We made sure that every iteration, the current estimate is stored in the old, so we can calculate the approximate error for each iteration, and that each iteration increases the number of trapezoids so that each loop creates a better approximation. So let's actually run this and see how it's going to look like. All right, perfect. So here we see that we ran 1, 2, 3, 4, 5 trapezoids. Here's the approximate error. Now the first one is usually off because we don't know what the old is. So since I defined the old arbitrarily, but everything else after it is accurate. Here we have the true error, and also here we have the integral. For one trapezoid, we have 2.079442, which is basically what we have defined here. So the difference between that number and the 2.15888 is that one white space that I showed you in a previous lesson. Now at 5 trapezoids, we saw that we went below 0.1% at 0.086477, and we have a area estimate of 2.15557. Now, as I mentioned, this code is defined in terms of a function, integration limits, and an error. So you can actually experiment with different errors. Let's actually see if we get an estimate that is below 0.01. Like how many trapezoids would it need to get us this type of estimate? So it would require 10 different trapezoids under this area, and we saw that we actually went below 0.01% at 0.009046, and the estimate is 2.158050. Let's experiment with one last error, which is 0.001, and see how many trapezoids it's going to require. In this case, we need 21 different trapezoids to get a estimate with this accuracy. So here we went below 0.001 at 0.000897, and here is the estimate at 2.158694. So you can see actually with this very, very simple, very effective technique that is only dependent on the equation of a area of a trapezoid, now we have bypassed the integration rules and we have an estimate here that is as accurate as the true value here, which we got using the integration by parts rule. So you can see the effectiveness of this rule. You also can see that for us to get this level of accuracy, we had to loop 21 times. In subsequent lessons, we're going to be seeing more accurate methods, which means we are going to be requiring less loops to converge to this type of accuracy. So that's it for this lesson, and I will see you in the next lesson.